in D, we will try and figure out exactly what distribution mu tilde has. So what we're asked to do is to let z tilde denote a random variable with distribution mu tilde, and then we're asked to characterize this random variable. More specifically, they ask us whether it is the difference of two exponential random variables as before. Now, given that they ask a question like this, we might guess, well, yes, it might be, or else why would you ask? However, let's just take a look at what they might mean by that. Previously, Z1, Zi was defined as the difference of C multiplied by tau I and the claim size. And since we know the claim size is exponentially distributed with parameter theta and that the inter-arrival times are exponentially distributed with parameter lambda, then we had that Zi was the difference of two exponential random variables with a moment generating function that we have written up here. Now, our question is Z tilde also the difference of two exponential random variables? Because it could be nice if it was. We always like to work with exponentially distributed variables. However, you can be quite sure that it probably does not have the same distribution as the Zi, because Zi are increments in a random walk where the net profit condition is satisfied, whereas the mu tilde distribution allows for the random walk to have negative drift, in which case ruin occurs in almost every outcome. So we won't get the exact same distribution in mu tilde as in mu. However, we might get something similar. So let's start calculating. And the way we do this is by considering the moment generating function of z tilde. So the moment generating function of z tilde is given as the integral of e to the alpha y with respect to the distribution mu tilde. And by abstract change of measure, we get that this is equal to the integral over e to the alpha y multiplied by e to the minus ry with respect to mu. And this in turn is just equal to the mean value of e to the alpha minus r z1. And what we can do now is recall the definition of z1, and since the inter-arrivals are independent of the claim sizes, we can split this up into the product of two mean values. In the first term, you have e to the alpha minus r multiplied by c tau 1. And in the second, you have the mean value of e to the minus alpha minus r multiplied by y1. And now let us just plug in what those are. So recall that in an exponential distribution, the moment generating function evaluated in alpha is equal to the parameter divided by the parameter minus alpha. So what you have here is, well, c tau is exponentially distributed with parameter lambda over c. So you have lambda divided by c divided by lambda divided by c minus alpha minus r multiplied by theta divided by theta plus alpha minus r. And what we can do now is use what we have from previous exercises where we calculated the value of r. So you can see that in this first fraction, if you just multiply everything by c, then you'll have lambda on the top, and then lambda minus c alpha plus cr. So let's just write this down. You have lambda divided by lambda plus cr minus c alpha, and then we have theta divided by, well, theta plus alpha minus r, where r is equal to theta minus lambda c. So the theta and the minus theta, they cancel, and then you just have lambda divided by c plus alpha in the denominator. And from part of the calculations in the previous exercise, we see that cr plus lambda is equal to theta c. So we have lambda divided by c multiplied by theta minus c multiplied by alpha, which is just alpha minus theta minus alpha, and you divide by c on the top and in the bottom, and theta divided by lambda over c plus alpha. Okay, and if we just move things around a little bit, you get theta divided by theta minus alpha multiplied by lambda divided by c over lambda divided by c plus alpha. And you actually see that this kind of reminds you of something that we've seen before. It kind of reminds us of the moment generating function of z1. However, it is not the moment generating function of z1 in alpha, but in minus alpha. And what this tells us is the fact that z tilde, in fact, has the same distribution as minus z1, which is then equal to, so z tilde has the same distribution as minus z, which is then given as the claim size minus c multiplied by tau I. What this also means is that if we want to simulate something, if we want to, I can't find it anymore. Well, we'll get to that in the next exercise. This is a very significant result when we think about what it is we wish to simulate, because we wish to simulate the Rouen probability, which was given as the mean value under mu tilde of e to the r multiplied by s at time of Rouen. And these can now be simulated using the sum of these increments until we achieve Rouen, which occurs with probability 1. So we now have an expression for those variables that we wish to simulate in order to find an estimate for the Rouen probability, which we will do in the next exercise. See ya!